In our last video, we took a refresh look at design for manufacturing, a critical step in the manufacturing process that ensures a part can be reliably and repeatably manufactured thousands or even millions of times. So if you haven't seen that full DFM intro video yet, I'll link to it down in the description if you want to check it out, because today we're walking through the full design for manufacturing checklist that our engineers use when evaluating plastic parts for injection molding. We'll go through each item in detail, what each one means, why it matters, and what questions you want to be asking throughout this critical and often overlooked process. If you want your own copy of our full DFM checklist so you can follow along, there's also a download link in the description as well. Okay, so in the simplest terms, design for manufacturability just means designing parts so they can be made reliably, repeatably, and cost-effectively without too many surprises. Again, we covered the big picture fundamentals in the last video, so today is all about the important details, so stick with me and use the chapter cards down below if you want to jump to any specific topic or section. A key step in the DFM process that helps avoid headaches down the road is running part flow simulation, which can tell us quite a lot about a part's design before steel is ever cut. First is the maximum pressure during filling. This is the peak pressure required to fully fill the mold cavity, and if a design requires excessive pressure just to fill the mold, then that's a red flag that should be addressed long before steel is cut. And that's because an excessively high filling pressure can lead to short shots, flash, or even mold deflection, which we definitely want to avoid. So early in this design process, you want to confirm that the mold can be filled with normal press limits without pushing the equipment or tooling to its edge. Next is maximum pressure during packing. After the cavity is filled, packing pressure is used to compensate for shrinkage as the plastic cools. If packing pressure is too low, or if it cuts off too early, you can end up with defects like sink marks or voids, which can affect both cosmetic quality and part strength. Thankfully, we use advanced mold fill simulation software that shows how the molten plastic will flow through the cavity, and we're looking for balanced, even fill here. If the flow is uneven, too slow, or racing through certain areas, you're more likely to see certain defects. Next, we graph and analyze the pressure during filling and packing. Ideally, this curve rises smoothly and predictably during filling. Sharp spikes or unstable pressure usually point to a gating, runner, or geometry issue. And those kinds of pressure swings often translate to inconsistent parts on the production floor, which can increase downtime. Clamp force estimation tells us how much force is required to keep the mold closed during injection. If clamp force is underestimated, you get flash. If it's overestimated, you may be using a higher tonnage press than necessary or placing unnecessary stress on the mold itself. So because of that, proper clamp force estimation is key for both part quality and tool longevity. Okay, now we move into thermal and shear behavior. During filling, the plastic heats up due to shear as it flows, and that rise in temperature can be helpful for flow, but too much heat can degrade the material or create burn marks. That's why temperature change during filling must always be reviewed and addressed as much as possible. Frozen skin is the result of the outer layer of plastic beginning to cool and solidify as plastic is still flowing elsewhere. If that frozen skin forms too early in the fill process, it can restrict flow inside the mold cavity, leading to all kinds of defects, most commonly short shots. But once again, simulation should tell us exactly where and when that frozen layer forms. As you've probably noticed and will see throughout this video, mold flow simulation is an invaluable tool throughout the entire DFM process. Next is the shear rate, measured in inverse seconds. High shear rates can lower viscosity, but also increase heat and material stress. Especially in parts that have thin walls, excessive shear can degrade the resin or create surface defects. Venting temperature is another critical item. When air is pushed out of the cavity through vents, those vents must handle the correct temperature range, since trapped gas can potentially lead to overly high venting temperatures, which causes burn marks, short shots, and surface defects. Next, we move into flow interaction defects. Flow tracer animation lets us visualize how different flow fronts move and interact inside the mold cavity. This is incredibly useful for predicting hesitation zones, trapped air, and where nits or weld lines will form. Speaking of which, air traps are areas where gas becomes trapped because the molten plastic seals off escape paths like vents. And if that trapped air cannot vent properly, it gets compressed and superheated, causing burn marks and short shots. Good DFM identifies where these traps occur and corrects them with venting or gate changes. Weld lines on a plastic part form when two flow fronts meet each other in the mold cavity. Some weld lines are cosmetic, others are structural weak points. And the exact location of weld lines must be predicted and reviewed to determine whether they're acceptable for the part's performance and appearance. And this is one variable that is heavily dependent upon each part's individual requirements. On a related note, weld line tracer animations show precisely where those flow fronts merge and how the material can continue to flow through the weld point. This helps determine whether a weld line falls in a high stress area, a sealing surface, or a cosmetic face. PVT chart analysis of weld lines takes that one step further by confirming whether the plastic at the weld line is at the correct pressure, volume, and temperature when it solidifies. If not, the weld line may remain weak and become a long-term failure point in that part. Next, we evaluate material solidification during cooling, including gate freeze. Gate freeze determines when packing pressure can no longer influence the part itself. If the gate freezes too early, you lose the ability to compensate for shrinkage, which leads to sinks, voids, or dimensional errors. Sink marks occur when thick areas cool and shrink more than surrounding material, and they'll show up most often at the ribs and thicker walled areas. Hotspots are regions in the part that retain heat longer than surrounding areas due to part geometry or cooling layout. These temperature imbalances lead to uneven shrinkage, warpage, internal stress, and longer cycle times. Now, you've heard me mention voids several times by now, and these are internal pockets created by unresolved shrinkage. They reduce part strength and often go unnoticed until testing or field failure, so simulation helps identify where voids are likely to form, so geometry or processing can be corrected early. All right, now we move into wall thickness and geometry control. Any thick areas of the part increase the risk of sinks and voids, so instead of making walls thicker for strength, it's usually better to core out material when possible and add ribs for stiffness when necessary. Thin areas create the opposite problem. If a section is too thin, the plastic may not fully fill before freezing. Thin walls also increase shear and surface temperature, raising the risks of burn marks or poor cosmetic quality. Uniform wall thickness throughout the part is the single most important DFM rule in plastic part design. Consistent thickness promotes even flow, uniform cooling, reduced warpage, fewer sinks, and shorter cycle times, and sudden thickness changes should be avoided whenever possible. Next are a few material-driven risk factors. Some resins simply do not flow well and require shorter flow lengths or thicker walls. If the part geometry demands long or thin flow paths with a poor flow material, filling may be inconsistent or impossible without careful design changes. Next, we move into gate strategy. As we've discussed already, if a gate seals off too early, packing pressure is cut off before shrinkage is fully compensated for, which leads to sink marks, voids, and density variation. So placing gates in or near thicker areas help pack those mass concentrated zones and reduce the risk of these defects, and proper gate placement is also one of the most powerful levers in part quality. In fact, some parts require multiple gates to achieve proper flatness, roundness, or overall fill. Multiple gates improve flow balance, but also introduce more weld lines, so there's always a trade-off that must be evaluated carefully. Gating can also be executed so that plastic impinges on steel rather than free-flowing in open spaces, helping to reduce jetting and moisture streaking, improving overall cosmetic appearance. Next, let's talk about draft, ejection, undercuts, and tooling ease. Draft, which specifically refers to the angle of the part relative to the parting line, determines how easily the part releases from the mold after the cooling stage. Without sufficient draft in the correct direction, parts can stick, scuff, or even crack during ejection. When surface texture is applied, additional draft is almost always required because texture increases friction against the mold surface, so underdrafted textured walls commonly show scuffing or ejection damage. But on the tooling side, tooling must also avoid thin steel conditions. Thin steel areas experience high stress and are prone to deflection, cracking, and premature tool failure, so part geometry should always support realistic tooling design that optimizes for mold longevity. Certain mold features like undercuts, lifters, and side actions increase tool complexity, price, maintenance needs, and cycle time. So during the DFM process, engineers should always ask whether such mold features can be eliminated or simplified with geometry changes. And if necessary, it's worth discussing alternative options like master action frames to help reduce mold complexity and cost as much as possible. And finally, we have advanced material effects. Crystallization in semi-crystalline polymers affects shrink rates, stiffness, and dimensional stability. This must be evaluated when tight tolerances or high performance is required. Fiber orientation also applies to fiber-filled resins like glass-filled nylon. system. During flow, fibers align along the direction of flow movement, and this creates directional strength, but also drives directional shrinkage and warpage, so gate placement and flow paths directly control fiber behavior and need to be carefully considered. Okay, I know that was a lot of information to take in at once, and if you're feeling a bit overwhelmed at this point, don't worry. An experienced injection molder will help walk you through this entire DFM process and advise you on the many decisions that need to be made to ensure the long-term success of your program. And while there are certainly a lot of variables to consider, as you just saw, by using this DFM checklist, you'll ensure that no stone goes unturned and hopefully avoid costly surprises down the line. Again, be sure to download your copy of our DFM checklist using the link down below, and if you'd like to learn more about how Crescent Industries can guide you through this complex DFM process, then be sure to reach out to us using the contact information down below and learn how we can help bring your injection molded part to life.